So you have a zinc specimen, you can able to see. So you have a width of 40 mm, a breadth of 2.5 mm, length of my element is 120 mm, right, for my specimen. So when I use this in my mission, what happens is you got different loads and some extension. You have the values. For 10 kilonewton, your extension is 0.15 mm. Similarly, it goes like this and it ends, right? So fracture occurs when the extension is 5 mm. So at the 5 mm fracture, it breaks, right? This is the case. The maximum load is recorded as 38.5 mm, so which is here. And you have to identify what is the plot for this. You have to identify what is the stress at the limit of proportionality, which means within elastic limit, you have to identify what is the stress developed. You have to identify what is the Young's modulus for the material. You have to identify what is the ultimate strength for the material, percentage of elongation, stress and strain, stress at the strain of 0.01. So when your strain is 0.01, you have to find out what is your stress. Similarly, extension, if the stress is 200 megapascal, this is what the entire problem is, right? So still now, we taken some problems related to what you can say, stress strain diagram, right? So நம்ம பார்த்த problem எல்லாமே பாத்தீங்கன்னா it is related to stress strain. So which is, so you have your y-axis and x-axis, right? Your y-axis is always stress and your x-axis is always strain. So but if you look after the formula, what is the formula for stress? Stress வந்து பாத்தீங்கன்னா force by area, right? So in this case, area we always consider initial cross-sectional area. We are not considering final. So அப்பப்ப மாறல area. So ஒரே cross-sectional area தான். அப்போ வந்து பாத்தீங்கன்னா இந்த area வந்து constant. This is constant, right? So this is constant. Similarly, I have strain which is equal to change in length by original length. That is my formula. So here change in length is also constant. So starting change in length is 120 here in this case. So we're going to consider the same 120. So there is no change in this L. L is constant here, right? In that case, I can write something like this. So stress is equal to P by some constant, which I can say that stress is directly proportional to your force. Similarly, strain is directly proportional to your change in length. In that case, instead of plotting stress strain, I can also plot this one, which is force by change in length. There is no difference. You know, change in length is proportional to strain. Your force is also proportional to your stress. This graph will be same. There is no difference in the graph. So here we have forces and extension, change in length. So I'm going to plot this two based on this, which means it is nothing but stress and strain diagram, right? There is no difference in this. So let me do that. So when I do this, this is how it plots. So you have different location, and each location at 10 kilonewton, what is the extension? I am plotting something like this. So I am getting a graph, a beautiful graph like this. Now I want to identify what is my proportional limit. So to identify proportional limit, you know that, so it should be linear line. Stress is directly proportional to strain. So it should not be some curves, something like this. So what I can do, I can keep a scale here, or I will just draw a line here. So you can able to see 10 kilonewton, 15 kilonewton, and 25 kilonewton is having a linear line. After that, your line is changing. It is non-linear, right? So my proportional limit is up to 25 kilonewton. This is my proportional limit. Okay. So now I identified what is my proportional limit. Maximum limit is 25 kilonewton. So that is my maximum force. And of course, this is under proportional limit, which means elastic stage. After this, it is going for a plastic stage. This one is ultimate stress, right, which is 38.5. So now I got what is my load. Based on this, I can also identify what is my displacement here, right? Change in length. So I know change in length and what is my load. I can identify what is my Young's modulus. So limit of proportionality is at 25 kilonewton. So I identify what is the cross section. Cross section area is already mentioned. Width and thickness is given. So based on that, my cross section area is 40 into 2.5, which is 100 mm square. So my force is 25 kilonewton. So stress is force by area. So force is 25. Of course, let me solve my problem in Newton and mm. So 25 into 10 power 3 you will have. And my area is 100. So I will get 250 Newton per mm square. That is my stress. Similarly, I can also identify what is my strain. Change in length from the graph, it is 0.35. So that is what this location. This location is, so when I just draw a line here, you can able to see this will be 0.35. So 0.35. So original length you know, which is 120. So strain will be change in length by original length. So I'll get 0.35 by 120, you will get 0.00292. So no unit for strain. Now we will identify what is the Young's modulus. So Young's modulus is stress by strain. So I am going to consider this two. So this one and this one. Let me divide it. So 250 by 0.0292, you are getting a value. This is the Young's modulus for the particular material, right? So this is how you will identify in an experimental way. Similarly, they are also asked for ultimate strength. Ultimate strength is maximum load by area. No change. Only difference is instead of 25, I am going to put 39.5, right? That is my maximum, I think so. 38.5. So 38.5 into 10 power 3 divided by area is again 100. I will get what is my max ultimate tensile strength. Ultimate is maximum. Whenever I say ultimate, it means maximum. Next, percentage of elongation. Same formula what we discussed last class. Final length, maximum minus minimum, right? Maximum is final length minus initial length divided by initial length. So before it starts, what is the length? That is what we are going to consider. So final length is 125. So why we consider 125 here? So if I consider this, maximum extension is 5 mm. My gauge length is 120. So which means my total length will be 120 plus 5, which is 125. So that is my value for this. Right? 125 minus 120 divided by 120 into 100. So I'll get 4.16%. So similarly, they also asked what is the stress at a strain of 0.01. So this is similar to identifying from the graph. So first I want to identify what is the change in length, because my graph is having only change in length and force. So let me identify what is my change in length. So you know strain is change in length by original length. So then change in length is strain value 0.01 into original length is 120. You are getting 1.2 mm. So now in the graph, right, 1.2 is somewhere here. I'm going to draw a line here. Sorry. So I'm going to draw a line here. So it cuts here. Then I am going to identify what is my load P. This is what I'm doing here. If I identify, you will get my load as 36 kilonewton. So from this, I can identify what is my stress. Stress is force by area. I identify what is my force. So what is my stress, right? Similarly, extension when the stress is 200 megapascal. So I'm going to clarify this. First thing is 1 megapascal is 1 into 10 power 6 Newton per meter square. So Pascal is Newton per meter square. It is not mm square. Okay. So which is 1 into 10 power 6 Newton, converting this meter to mm. So which means meter, 1 meter is 1000 mm. So which is 10 power 3. So 10 power 3 square mm square, right? So it's just 10 power 6, right? So 3 into 2, 10 power 6, 10 power 6. So which means 1 megapascal is 1 Newton per mm square. So 10 power 6, 10 power minus 6 gets cancelled. When you go to the numerator, it will be 10 power minus 6, right? It gets cancelled, right? So this is your 1 megapascal. Here, if it is 200 megapascal, which is 200 Newton per mm square, right? This is 200 Newton per mm square. Directly I can write, right? So I'll identify what is my force. Then force is 20. I'll take 20 here. I will draw a line. So and then I'll go towards downward. So I'll identify what is my change in length, right? My change in length is around 0.3. So they are asking extension. That is what we are indicating here. So this is one problem related to some laboratory point of view. So when you solve this in a practical way, we will be doing something like this. So next we will go for few more topics. True stress and normal stress. So this is how we discussed in last the problem also. There is something called as true stress or actual stress. So what it means is when you have a specimen, so when you apply a force, the specimen will have increase in length but decrease in cross section, right? My cross section is decreasing. So which one we have to consider for my stress? So we always use force by initial cross sectional area, which is A0. But when you apply a load, you can't identify what is the area. It is very, very difficult, right? You can't even keep a strain gauge. And it is, of course, very, very difficult to identify when the time of loading. Only thing is I can identify at the time of braking, right? At the time of braking, I can measure, which will be final cross-section area. So normal stress is forced by initial cross-section area. True stress is forced by final cross-sectional area. So when I plot my true stress, you will get something like this. Rupture will be like this. So last class, someone asked why load is reducing. So when I apply a force maximum, when at the time of brake, why the load is reduced instead of increasing? The answer for you is this. It is because of this one. Real one, your load is increased. It is not reduced like this, right? Because your area is reduced, right? Your area, final area is very, very much less. Because of that, your force, whatever we required is to that limit, which will be a maximum one. But when I consider initial cross-section area, there is a decrease in my curve. Because of this alone, that you can able to see that difference, right? So it is losing the elastic property or withstanding property that also reduces the curve. But when you consider mathematically, we have to speak like this: AF. So because of we are always considering initial cross-section area, your curve is like this. If I consider final cross-section area, my curve will be towards upward direction. That will be maximum. But this is highly impossible. This is not possible to find. So there are lots of reasons, because for a brittle material, it is difficult. For a ductile material, it will be different. Each material will have different type of expansion. So because of that, they always consider initial cross-section area. They won't consider that final cross-section area. And of course, while measuring also, you will lose even 0.1 mm. You will make a mistake in measuring, right? So that comes the difficulty. So they always consider initial cross-section area to solve any type of problems. So next, we'll go for next topic called as factor of safety. If I want to design any material, factor of safety is very, very important. What it says, for example, let us consider a lift in Saravana store. So in Saravana store's lift, it says that maximum 15 persons you can go. But in our case, what we will do, we will be going 25. So the lift carries more than this. So even at 25%, the lift will move and it will work properly. But it is mentioned in the lift, it is mentioned that it is applicable only for 15. This is what we call it as a factor of safety. What is my factor of safety here? So maximum it can withstand 25. And my person, what they mentioned is 15. So what is my factor of safety? So it is around 1.2 value. So this is factor of safety, right? For any material, you have to identify factor of safety. You can't design any material directly to that particular load because it has to withstand in a large way. Factor of safety is ultimate stress by allowable stress. So there are two things. Whenever I say ultimate strength, it is for brittle material. For any brittle material, we consider ultimate stress. For ductile, we consider yield stress. So yield stress by allowable. So there is a difference. So yield is within elastic limit. Okay. So for brittle material, we always consider ultimate stress. For ductile material, this is for ductile. For ductile material, we consider yield stress. So allowable, the allowable are working stress. What stress you are working, that gives you what is the factor of safety. So how to use this factor of safety? So these are the consideration to identify your factor of safety. So very, very important. So you can't judge anything related to this. You can't just take some value and you can't put that as a factor of safety. There are some consideration, right? So for example, you can see a plane, right? So what is the size of my plane? It's very, very big, right? Maybe one room size, right? One room size will be the compartment, will be one compartment, which means my factor of safety is around 20 or 25. So if I increase my factor of safety, my dimension in my object will also increase because my stress is forced by area. My formula is stress is forced by area. I will just think about it. I have to reduce my stress, which means I have to increase my area. When my area increases, automatically my stress will decrease. There is no possibility of load because load is an input value. So you can change my cross section based on something. So when I increase my cross section, my stress is decreasing. But what about the area? So since the area increases, the size is also very, very bigger. So that's why your planes are very, very bigger in size. So you can't take the same 20 factor of safety for a bicycle. So என்ன ஆகும் பைசைக்கிளோட சைஸ் டயர் சைஸ் டயர் வந்து நீங்க கீழே விடக்கூடாது. அப்போ வந்து டயரோட வித்து ரொம்ப 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 பெருசா இருக்கும், ரைட்? ஸோ அப்போ வந்து ஓட்டுறதுக்கு கஷ்டமாகவும் இருக்கும். அது தட் இஸ் டிஃப்ரெண்ட் கேஸ். ஸோ தட் இஸ் சம் ப்ராப்ளம். ஸோ வி கான்ட் யூஸ் இட். ஸோ அதுக்காக வி ஹேவ் சம் கன்சிடரேஷன். வாட் ஆர் தி கன்சிடரேஷன்? ஃபர்ஸ்ட் ஒன், uncertainty in material property, which means whenever I take any material, so for example 100 or material, raw material வருது, right? What they will do, they will test that material. So property எப்படி இருக்குன்னு பார்ப்பாங்க. So property, if it is very, very good quality, then they will reduce the factor of safety. If they are not happy with the property, they will increase the factor of safety. Right? That is one condition. Condition 2, certainty of loadings. Sometimes there is no possibility of identifying what type of load acting on a particular missions. So for example, the same case, if I consider a plane, turbulence form ஆகும், திடீர்னு cloudy problem இருந்ததுன்னா, rain problems இருந்ததுன்னா, load எப்படி act ஆகுதுன்னே தெரியாது. So it is very, very difficult to identify. So since it is very difficult to identify loads, I can increase my factor of safety. If the load is less, I can easily identify, then I can decrease my factor of safety. Uncertainty of analysis. You can't judge what will happen if you are doing a particular thing. Then you can increase the factor of safety. If we are easily identify, this is what the problem is. Problem வந்தா இதுதான் வரும். So மற்றபடி வர வாய்ப்பே இல்லை அப்படின்னா, then you can reduce your factor of safety. Next, number of loading cycles. So when I say loading cycles, so how many times you are working it? So continuous work ஆகுதா இல்ல விட்டு விட்டு work ஆகுதா? So that is also one consideration. Type of failure. Type of failure depends on different conditions. Temperature problem, environmental conditions, right? So that type of failure. So different failure condition. So water பட்டுச்சுனா waterproof அந்த மாதிரிலாம் இருக்கு இல்லையா? So that also deals with factor of safety. Then maintenance requirement, right? Whether you have to maintain that continuously, right? ஒரு குறிப்பிட்ட object. For example, if I consider a pen, you don't need to maintain a pen. There is no purpose of using any maintenance for a pen, which means there is no factor of safety. It will be very, very less, right? So of course, nil factor of safety. But if I consider any missions, lathe machine or any machine, it has to be maintained, right? So அப்பப்போ மெயின்டெனன்ஸ் பண்ணணும். பைக் எடுத்துக்கோங்க, அப்பப்போ வந்து சர்வீஸ் விடணும். சர்வீஸ் இல்லைன்னா பைக் வந்து ப்ராப்ளம் கொடுக்கும். அப்போ அந்த மாதிரி இடத்துல you have to consider some factor of safety, right? Next, importance of members to structures integrity. It means some component will transfer force. For example, like a gear. So gear பார்த்தீங்கன்னா ஒரு ஷாஃப்ட்ல இருக்கிற பவரை இன்னொரு ஷாஃப்ட்டுக்கு ட்ரான்ஸ்ஃபர் பண்ணும். It will be something like this. We have two circles. If one is rotating, other will also rotate. So this is how it will transfer. So when it transfers, larger one rotates, one rotation போகும்போது smaller one will rotate 2 times. So that is how you have a gear in your bikes, right? So this structure integrity, so இதுல வந்து contact problem ஏதாவது இருக்கலாம், right? So அந்த மாதிரி கேஸுக்கு you can consider your factor of safety. Very, very important, life and property, right? Anything you buy, it should be risk to life. You have to increase the factor of safety. If it is not affecting anything, you can decrease your factor of safety. இது எல்லா கன்சிடரேஷனும் very, very important is this. So ஒரு சேர் வாங்குறோம், சேர் உடஞ்சிச்சுன்னா what will happen to us? ஒரு சின்ன கேஸ். So maximum லைட்டா முதுகு வந்து வலிக்கும். That's it, right? But plane crash ஆச்சுன்னா உயிரே போயிடும், right? So life. So that is very, very important. So your factor of safety should be less in chair, very, very, very much higher in your aeroplanes. So that is what is important. Then influence on machine functions. How a machine is connected to other, right? இதெல்லாம் ரொம்ப less. It is not that much important. So mainly these are the considerations. So you have to consider all these terms if you want to identify a particular value or factor of safety value க்கு இதெல்லாம் வந்து important. Now let us go for a simple problem. You have a hollow steel which is used to carry a compressive load of 160 kilonewton. So compressive load is 160 kilonewton. Yield stress is given, which is 250 Newton per mm square. Factor of safety is given, which is 1.75 and is used in a design. There are 3 classes of tubes. So when I say tube, external diameter is given, internal diameter is not given, but thickness is here. How to identify your internal diameter? So if I have two circles, larger one and a smaller one, external is 101. But when I consider internal, they are given thickness. Right?
External minus thickness.
So if I consider this as D naught and the inside one as DI, right? So D naught is equal to DI plus 2 times your thickness. Any doubt? Because your thickness here plus thickness here. So thickness plus DI plus thickness. So that will be your D naught value. So this is the formula to identify what is the diameter, internal diameter. So thickness is given, external diameter D naught is given, we can identify DI. So what will be my DI? DI will be D naught minus 2 times of thickness. Thickness is this. We can solve this in two ways. Number one, consider any one material class, identify your thickness, find out what is your DI, then calculate what is the area. You have D naught DI. You can identify what is the area, cross-section area. Then you can identify stress. It is somewhat lengthy process because you have to do for all the three. Easy processes, let us identify this as a variable. We will identify what is the cross-section area. Then we will choose from this. Right? That is the easy process. Let me go for that. First, I know what is my yield stress, which is 250 Newton per ohm square. My factor of safety is also known, which is 1.75. So we discussed the formula. What is the formula? Factor of safety is equal to yield stress by permissible stress. That is the formula. So now I need permissible stress. This is what my stress is. So permissible stress is yield stress by factor of safety. Right? Just opposite. Right? So what happens? My yield stress is 250, factor of safety is 1.75. I'll get what is my permissible stress. So now you know the formula. What is the formula for stress? Stress is force by cross-sectional area. I identify. So stress is 142, which is here. Force is given, which is 160 kilonewton. So as earlier we saw this in Newton and mm. So 160 into 10 power 3 divided by area. Right? We'll identify what is the area. So my area is 160 into 10 power 3 divided by 142.857. So I'll get an area of this. So now I'll go for the formula. So it's a tube. So my formula is pi by 4 d square minus d square. D is the outer diameter, d naught. Small d is inner diameter, di. Right? So I know what is my outer diameter, which is 101.6. It is given. I can apply that. Only unknown is small d square. Right? We can identify from there. Okay. So I'll just substitute it. Pi by 4, 101.6 the whole square minus small d square is equal to this area. Cross multiply and find out the value of d. My d is 94.32. If that is the case, what will be my thickness? Formula will be capital D minus small d divided by 2. Right? Any doubt on this? Capital D minus small d by 2. When you do that, you will get 3.63. I have this 3. Which one I can choose? We always choose lighter, which is a simple, small difference with the value. So instead of 3.63, here it is 3.65. So you have 0.02 mm difference. That is enough. We don't need to identify what is maximum, medium or heavy. Because as an engineer, you should think about material. So if I choose heavy, you can choose it. Of course, it can withstand more strength. But what about your material? You lose lots of material. The company won't get much profit. So which is better is this is, because we already mentioned a factor of safety. And what we calculated is around 3.63. So 3.65 is better than 3.63. So that is enough. If I go for 4.05, I lose profit. As a industrialist, if I think, I lose profit. This more profit. So this is the best way of choosing it. So we'll stop from there. So what happens if you have different materials here? So let me consider. So you have section 1, section 2, section 3. All are different areas, all are different length, right? In that case, let me consider all are having same material property. What happens? You just separate this as a simple parts, right? Identify it separately. So portion 1, stress, you know. Portion 1, strain, you know. Change in this PL by AE. So del L is PL1 by A1E. Right? For portion 2, do it separately. Your force is always same. There is no difference in your force. So stress for portion 2, again, PL2 by A2E. Since area is different, A2. See, here in all the cases, material is same. If your material is different, then instead of E, this will be E2. Right? Third one, do it separately. PL2 by L3 by A3. So if you have 3 different types of materials, different cross section, you can separate it one by one as a separate portion. Find out what is the change in length for each portion separately and add it. So this gives you the answer for that particular varying cross section problems.